In this session, we will talk about the origins of scientific method before we proceed to basics of scientific method. In the next chapters, it is based on the study of publication of Betz, and this, in this study, this is the reference. So let's take a look at the origin of the scientific method in history. We try to understand the world around us, by our sensory organs, by looking, by hearing, by touching, by tasting, whatever. And alchemy was a discipline, it was a precursor to the modern scientific discipline of chemistry, we can say that. It has been like a semi-science at earlier, at the beginning of these approach to perceive the world around us. In medieval Europe, the fundamental stuff of the universe viewed as air, earth, fire, water, and these all make the foundations of alchemy. Now in modern Europe, the fundamental stuff of the universe is energy and mass, atoms and molecules, fields and particles, chemistry and physics. And this is the modern version of, let's say, or advanced version of alchemy. Maybe we can say that, or a different, it's the modern scientific structure. Evolution of mathematics was also important because it provides the necessary tools for chemistry and physics. Modern science of mathematics has important historical roots in Egyptian, Greek, and Arab geometry and algebra. But algebra and geometry were not integrated until the 1619s, when Descartes created the modern mathematical topic of analytic geometry. And the modern topic of calculus created in 1693 by Newton, because he added the differential calculus of infinitesimals to the analytic geometry as well. And about the same time, and independently, Leibniz contributed the ideas of integral calculus as well. Then the modern discipline of mathematics intellectually grew in the 18th century as mathematicians built upon a modern analytical foundation of geometry, algebra, calculus, vectors, and later set theory. How do we perceive the nature? And before the 17th century, nature was merely a manifestation of supernature, and it was basically the world of religions, and the supernatural and unobservable things dominate the perception of nature in the human. After the 17th century, nature now is only what is observable in the world. So this is what we understand from nature. It's not, nature is taught about, described, and explained through experiments and theory and scientific paradigms now. No longer we live in a world of superstition and magic. We live in a modern world of science and technology. So there is no more superstition or magic here in our world. So when we take a look at the roots of scientific method, we cannot say that there was a really scientific method as we know today existed before Newton. Before Isaac Newton's grand synthesis of mechanics, there was not science, at least not as we know it before. Okay. Science began in that intellectual conjunction of research of 6 particular individuals: Copernicus, Brahe, Kepler, Galilei, Descartes, and Newton. For the first time in history, all the component ideas of scientific method came together and operated fully as an empirically grounded theory. They worked in different times, but let's say maybe in a few hundreds of years of span. But when you combine all of these studies together, all of them makes scientific method in total. A scientific model that could be verified by observation was proposed by Copernicus, and then a precise instrumental observations to verify those models was proposed by Brahe, was carried by Brahe. Theoretical analysis of experimental data was made by Kepler, and then scientific laws generalized from experiments has been driven by Galilei. And then we need mathematics for that to quantitatively express theoretical ideas. Descartes and Newton contributed to that. And finally, theoretical derivation of an experimentally verifiable model has been proposed by Newton in the end. We will briefly take a look at them one by one. Copernicus proposed an idea. Actually, it was a revival of an ancient idea that the universe should be modeled with the sun at the center and not the earth in the center. It is like the contradiction between sun-centric view and earth-centric systems. Copernicus' model challenged an older and then widely accepted model of Earth-centered system, which had been refined by this scholar, Greek scholar Ptolemy of Alexandria. Don't confuse him with the King Ptolemy of Alexandria, because they are different. We're talking about the scholar here. King Ptolemy lived in the era of Euclid. So we're talking about the scholar here. The Ptolemaic model had the Earth as the center and the Sun and planets circling the Earth. The motions of planets and Sun orbiting around the Earth was theoretically not elegant. It was neither simple nor direct in explanation. Copernicus argued that if all the planets were upon circles around the Sun, then the model could become elegant. What do we mean by elegant here? It could be more simpler and without added complexity to explain this phenomenon. Like you can say that it corresponds to maybe Occam's razor. So for going for the simpler explanation here. You can say that maybe it is the approach of a theoretic scientist here. Then came Brahe. Over the course of his life, he built several observatories and constructed measuring instruments larger and much more precise than previous instruments. He was a curious person, really. And curiosity is an important attribute or property of a scholar, of course, or scientist. These were astrolabes 10 times larger than the previous astrolabes. This precision of measurement provided data accurate enough to determine between the two theoretical models of the planets which in fact was real. Which one is real? The Earth-centric view or the Sun-centric view? We can say that Brahe was an experimental scientist and also an entrepreneur, because this tells us the importance of funding in research, because you need lots of funding or money to build such or to have such instruments. In historical perspective, we can view Brahe as a great experimental scientist because he understood that it was the precision of measurements that was the key to determining which model was correct in reality. This understanding by an experimenter as to what experimental data is critical to theory construction or validation is the mark of great experimental scientists. This is a key process in scientific method. We can say that a precise experimental verification of a theoretical model of nature by improved scientific instruments. Brahe made many astronomical measurements, and in 1600 he hired a mathematician, Kepler, to analyze all these data. Can we say that it was the first big data analysis in history? Maybe. Because Brahe was unable to or incapable of analyzing that data, because he that's why he sought help of a mathematician. To analyze means to abstract the underlying form of the data and to generalize the form so that the data from the additional new observations would fit into that form, like an extrapolation or like regression analysis. Analysis of data is the connection of observation to theory. But unfortunately, Brahe died unexpectedly on 1601, and Kepler continued working on analyzing Brahe's measurements, even though not getting paid on him anymore, just because of his curiosity here, because he was interested in the topic as well. By the late, after 1 year or something, Kepler found a law that nicely fit in the planetary data. Planets sweep out equal areas of their orbits in equal times. Here was the law of nature. It was a phenomenological law, a law of nature which nature follows, and also a quantitative law as well, which you can measure not only qualitative, not only based on observations, but also on measurements. Kepler understood that this law was a property of elliptical orbits. Copernicus' model had used circular orbits, in fact, but Kepler saw that in reality planets followed elliptical orbits, not circular orbits. By the end of the year, Kepler completed a new manuscript called Astronomia Nova, describing those elliptical orbits, but this was not published until 1609 due to legal disputes with Brahe's heir over the ownership of Brahe's data. Can we say that it could be the first dispute for intellectual property rights in science? Maybe, because it could be interesting. This quantitative formulation of a law of nature was a major step toward scientific method. Scientific method consisted not merely of qualitative observations of nature, but also quantitative measurements and quantitative laws depicting the underlying form of the measurements as well, which are called the physical laws of a natural phenomenon. Just before Kepler's publication of Astronomia Nova, the telescope was invented in 1608 in Netherlands, and learning of this invention, Galileo Galilei in Italy made a telescope that same year with 3-power magnification as well. You see the importance of instrumentation here again. He used it to observe the moon and the planets. He was the first to observe the moons of Jupiter, a large planet with 4 moons circling it, and this was a clear analogy to Copernicus' solar model, with the sun in the center of planetary orbits as Jupiter as the center of its moon's orbits. Galilei published his first astronomical observations in 1610 as Sidereal Nuncius, like in Latin, I cannot pronounce it correctly. And the double impact of Kepler's elliptical orbits and Galilei's moons of Jupiter sent Ptolemaic model into dustbin of intellectual history. With this much of pressure, the Earth-centric view was obsolete. Unfortunately, from 1612 to his death, Galilei was accused and denounced as heretic by the church and stayed at house arrest for the remaining 16 years of his life, unfortunately. But he kept studying there. And Galilei went on to establish the first scientific laws of physics. He performed experiments about motion and gravity and inferred new physical theory based upon experimental results. He pioneered the scientific method of doing quantitative experiments whose results could be generalized in mathematical expressions. Scientific method was exemplified in Galilei's approach: physical experiments on observable objects, measurements of relationships, analysis of measurements, formulation of theory as a phenomenological law of relationship between objects. These are the key steps or important parts of scientific approach. The next step in the emergence of the scientific method was to improve the language of the quantitative analysis used here. We need help from mathematics. The invention of analytical geometry and calculus and their application to the expression of physical theory. Descartes was the contemporary of Galilei and made a very major contribution to advancing mathematics. He conceived the analytical geometry, adding algebraic expressions to the classical geometry of Euclid as well. And Descartes proposed to describe a space with basic vectors like x, y, and z, the three-dimensional space that we use today, so that every vector was at right angles with each other. Then any point in space could be described by 3 numbers, x, y, z, as their coordinates, as projections on those vectors. What Newton would add later is another time dimension t on this, then it would be total. Motion of a particle in space could then be described as the succession of points occupied by that particle as time t elapsed. This analytical geometry would provide the critical mathematical representational basis for physics, and it will help Newton's for Newton's calculus as well. Without analytical geometry and calculus, modern physics would not have been possible. Then came Newton. Descartes' combination of geometry and algebra enabled a quantitative description of space. This would allow Newton to combine the Galilean physics with that Cartesian geometry. It will then be called as Cartesian geometry. The Descartes' work is called Cartesian geometry now. And also with Kepler's astronomical ellipses to create combining all of them together to create a dynamic model of the solar universe. After all that time, from Plato, Aristotle, Augustine, Bacon, Copernicus, Brahe, Kepler, Galilei, and Descartes, very, very important people, all of their work together finally became very, very meaningful and useful at this time of history. Then finally, the stage of history was set for Newton and his grand scientific synthesis of mechanism. You see that, yes, Newton did a very important thing, but see how it accumulated, or it was a cumulative work of many important scholars and scientists. Then he published the Philosophia Naturalis Principia Mathematica in 1687, and he set three universal laws of motion here. Law of inertia, the motion of which we are very familiar now. We studied these in the middle school, I guess. And the motion of a body is constant unless acted upon by an external force. This is the law of inertia. And law of force is the effect of an external force upon a body is to change its acceleration proportional to the body's mass. Okay. And finally, the law of action-reaction. For every action force upon a body, there is an equal and opposite reaction, which is called reactive force. Now, it's maybe interesting that, do we remember this scientist as well as Newton? He is Robert Hooke. Maybe he is familiar to me with his Hooke's law that I've seen in physics courses in high school, I guess, about the extension of those strings here. He was also another scientist, another important scientist, but there was a dispute between Newton and Hooke. There was a disputed claim about who first discovered the quantitative law of gravity. Robert Hooke experimentally demonstrated it had the quantitative form of diminishing with the square of distance here. Apparently and independently, Newton also had formulated the law of gravity as diminishing by the square of distance as well, you see, at around the same times. However, Hooke insisted upon acknowledgement by Newton that Hooke had first discovered the law. I mean, Hooke maybe argues that Newton took it from him. Newton refused this since he believed that he had not learned it from Hooke. Now we see that again. It's a phenomenon in scientific study. In the organization of science, scientific credit and prestige goes to the person who first to discover or explain a natural phenomenon. And how can you say that you are the first? Just by publishing. So if you don't publish your results, it means that even though Hooke was right, maybe we don't know. Since he didn't publish it, he couldn't claim a strong. He couldn't come up with a strong argument here. He had disadvantage here. So publishing, it tells us about the importance of publishing in this scientific domain. Scientific method as an empirically grounded theory. This is important, and the critical component parts of the scientific method are observation and experimentation. See? And instrumentation and instrumental technologies that have been used by Brahe, as you remember, and theoretical, we need funding as well, and sophisticated instruments here. The theoretical analysis and model building is important, and theory construction and validation next, and paradigm development and integration of other theories and components here. So, central to the scientific method is the construction of theory of nature based upon and validated upon experimental observations of nature. Knowledge which is not empirically grounded theory is not scientific. This is an important issue. So it should be grounded on measurements. One calls the research approach of experiments on nature as an empirical approach in scientific research. This is called empiricism. And one calls the research approach of theory construction about a nature, which is called a theoretical approach. In scientific research, it is called theoretical work. So you can see that you can compare general principles here and approach the problem in a theoretical manner, or you just collect the data, abstraction of particular facts here, and go for theories here. It is called empiricism. So you can go both ways, either this way or this way. So these are the two main types of scientific application of scientific approach. Okay. Now we finished the origin of scientific method. Then we will proceed to the scientific method, modern scientific method properties in the next session. This part is heavily from this study. If you want to read the full paper by Betz, this researcher, you can download it here or see it from here.